We'll be starting in 5 to 10 seconds now.
Okay, ma'am.
Priyanka, madam, you can start.
Okay. Good afternoon, everyone. On behalf of All India Sri Shivaji Memorial Society College of Pharmacy and Principal Dr. Ashwini Madgulkar, Madam, I, Priyanka Kandhare, welcome you all to today's webinar entitled with Role of H1 NMR in Structural Elucidation. Today's webinar going to be enlightened by our distinguished speaker, and it's my privilege to introduce Dr. Vaishali Shinde. After completion of MSc degree in 1996 from Pune, Professor Vaishali pursued her doctoral work at chemical under Dr. Raghunath Mashelkar and obtained her PhD degree in 2002. She has postdoctoral research experience in the group of Professor Axel Muller at the University of Beirut, Germany in 2006. She had joined Department of Chemistry in as an assistant professor in 2003 and subsequently promoted to full professor in 2015. She has a 20-year teaching experience and a research work experience. Her group is mainly working in the area of a carbohydrate synthesis as well as natural product synthesis and glycopolymer material. Her research work also involved in a various sugar polymer like thermosensitive and glycopolymer and smart gels. The 10 students have obtained the PhD degree under the supervision of her. Now they are working with her as a doctoral work. Professor Dr. Shinde has the recipient of the DST Biocast Fellowship under the Emirates program of a European Commission to visit the University of Uppsala, Sweden in 2013 and University of Bologna, Italy in 2014. She is a young associate and fellow of the Maharashtra Academy of Science in 2018. She is actively involved in the organizing international and national webinars and workshops and as well as invited for the same. Professor Shinde has invited as a member of an academic council of various universities, especially from the Pune and Karnataka states, and member of the board of a student various autonomous Maharashtra. With this brief introduction, I invite Dr. Vaishali Shinde to start with the scientific session. Over to you, ma'am. Thank you.
Good afternoon, all of you. Whether I am audible?
Yes,
Yes,
madam,
ma'am.
you are audible.
Yeah, thank you. I'm very thankful to Dr. Madgulkar ma'am, Dr. Bandari sir, Dr. Damle madam, Dr. Gandhi, and Priyanka as well for introducing me nicely.
Ma'am, thank you.
And thanks for your invitation too. So I am here to focus on my area today is focus on the H1 NMR spectroscopy as a tool for the structure elucidation. From yesterday, your webinar is going on. I already had 2 sets. This webinar I am dedicating to my gurus, my teachers, Professor M.S. Wadia, Professor R.S. Mari, Professor D.D. Dhawale. So they have played very important role to produce interest in NMR spectroscopy with me. So let's start with this today, H NMR spectroscopy. Friends, yesterday you have been listened the first lecture on TLC, chromatographic techniques. So what do we do, the chemist or any pharmacist? They synthesize the compound, and once they will synthesize or isolate from the natural product, they have to elucidate the, they have to first purify the compounds by using the techniques, just like yesterday we have been very good session by on this chromatographic technique. So by chromatographic technique, one has to purify the compound. After the purification, the organic chemist first will submit the samples to the UV-IR, if and then H NMR spectroscopy. So let's go towards the H NMR spectroscopy. So the techniques we do in scopy, the sample. Then this sample we have irradiated with the electromagnetic radiation. The molecules in a sample absorbs the radiation and they will go to the excited state.
Sorry, madam. Sorry to interrupt. Can you please shift the mode to the presentation mode, because here the slides are appearing too short. So the usual full screen mode.
It's a presentation mode only, ma'am. Presentation mode?
No, I don't think so, ma'am. It is not full screen, basically.
Okay, okay.
It's okay.
Or can we stop sharing and reshare it and go back to the original?
Yes, yes, sure.
Yeah. Ma'am, can you please share? Hello, Dr. Shinde. Can you please share?
Yes, yes, sure, sure. Now it's okay?
Yeah, madam, please click on the full. Yeah. Now it's perfect. Thank you.
Shall I start now?
Yes, madam.
Yeah. So okay. So as I said, Spectroscopy is nothing but we are irradiating with some electromagnetic radiation. Sample molecule will absorb the radiation, go to the excited state, and what the spectrum we will get, we call as absorption spectrum. When the excited state molecules come to the ground state, we call emission spectra. So UV visible, IR spectroscopy, and NMR. These are the three basic spectroscopic techniques that the organic chemist is usually used for the structure determination. From the UV visible spectroscopy, one can get the presence of chromophores, or if the compounds contain conjugation, in terms of whether the molecules has the alkenes, alkynes, or aromatic or carbonyl compounds, one can detect from the UV visible region. From the IR spectroscopy, we confirm the functional groups present in a molecule. Yesterday, we have already listened very good lecture on this IR spectroscopy. We can confirm the functional groups such as the hydroxyl groups, NH, CH stretching, we also get it. Carbon-carbon triple bond, carbon double bond, different carbonyl group. Even the fingerprint region is very useful for the IR spectroscopy. The H NMR spectroscopy, one can get quite a good kind of information, like the number of different types of hydrogen we will get. Not only the types of hydrogen, relative number of different types of hydrogens, their electronic element, whether the hydrogen is attached to the electron withdrawing group or not. Then we do also get a spin-spin coupling, so which will give the multiplicity to the signal. Nowadays, in this pandemic situations, even we are unable to contact neighbor, but in H1 spectroscopy, the molecule, the one hydrogen is coupled with its neighboring hydrogen. So neighbor to neighbor relationship, one can very good, we can see in a H1 spectroscopy. Not only the H1, along with H1, if we have the C13, N15, 19 fluorine, or 31 phosphorus, this will give again quite a good structural aspect to the molecules. All these techniques are mutually complementary with each other. And the combination of this, along with mass spectrometry, forms a very powerful device in the determination of structure of organic and biomolecules. I know, friends, I'm here in between you and your nap. So it's my tough job to keep you awake. So the outline of my talk today is why NMR is important. So it is very good, powerful tool for the structural determination. And what NMR can do for us? So it provides the information for the hydrogen atoms in the molecules and how you can use it to solve your problems. My final topic, this final point I'm trying to elaborate in my talk. Moving to the discoveries and developments in NMR spectroscopy, up till now, there are 4 Nobel Prize has been grabbed in a different subject like the chemistry, physics, and medicine field as well. When we think about the NMR spectroscopy, this NMR spectroscopy has been invented or discovered in 1945. The first Nobel Prize has been given in the subject physics in 1952 to the 2 groups. One is Dr. Bloch and Dr. Purcell. They both are working in different universities, different labs. One is working in water. Dr. Bloch, he is working in a Stanford University and working on the water molecules, while Professor Purcell, he was working in Harvard University and he was working on the paraffins. So they have done the very good work in the area of NMR, and they have been awarded with the Nobel Prize in 1952. Next Nobel Prize has been given to the Ernst. He is from the Zurich University, and he received the Nobel Prize in 1991 for the methodology for high resolution NMR. Next Nobel Prize is coming to the, again in a chemistry, to the Kurt Ulrich in 2002. Again, he is from the Zurich, Switzerland, and he received the Nobel Prize for his work in three-dimension structure determination of biological molecules. Next, in 2003, the NMR Nobel Prize goes in a medicine subject to the Paul Lutherberg and Peter Mansfield. Both are working in two different universities. One is Illinois and other Birmingham, and they have done a very nice work in the area of magnetic resonance imaging. It's an MRI technique. Friends, you are already aware that in many of the hospitals, this technique is already there in many hospitals, where we can scan our whole body. Here I have given the one photograph for the MRI of scan of skull. You can assess the soft tissues present in a skull, like the eyes, near the muscles near the eyes and brain. The name has been given as a magnetic resonance imaging, not NMR, because the common people is afraid of the word nuclear. So they have changed the name as a magnetic resonance imaging. My next slide shows the development in NMR spectrometer. The first photograph is shown as continuous wave NMR spectrometer. It's a 40 megahertz machine, and it has been fabricated in 1960. Friends, here they have used the electromagnet. After few years, maybe in the 20th century, the magnet has been transferred from the electromagnet, it goes to superconducting magnet. And here there is a drastic change from 40 megahertz, they are going to the 500 megahertz machine. I have shown here one of the slide where in the same slide, I have shown the first NMR spectra of the ethanol, which is recorded by the three scientists, Arnold, Dharmatin, and Packard. And we all Indian are very proud movement for this, because the one of the scientists, Dharmati, he is the Indian scientist. After doing work in abroad, he came to the again India, and he has been work in a Indian institute. The same spectra, ethanol, now if we scan in a superconducting, by using superconducting magnet NMR, see here we are getting very well resolved NMR of ethanol, where you can observe 3 lines around 1.1, then at 3.8, it is again some splitted signal and one more signal. So the same molecule, if you scan differently at high resolution NMR, you will get a more information. Let's look at the background and theory. You know, nucleus contains protons and neutrons, while the outside the nucleus, we have the electrons revolving in a different orbitals. Nuclei with an odd mass number or an odd atomic number, they have they possess a spin. We also call it a spin quantum number or angular momentum. For example, hydrogen, it's having the odd atomic number and it's a 1:1. Deuterium 2:1, carbon 13, 19 fluorine, phosphorus 31, all these contain, these has some spins. But if you look at the carbon 12, which is a normal isotope of carbon, as its number of proton, neutron, and electrons, they are 6, 6, and the spin will get cancelled. So carbon 12 does not have any spin. So such nucleus, the nucleus with a spin, if it's always spins, and this charged particle will behave as a magnet. it creates some magnetic field. In absence of external influence, the magnetic poles randomly oriented. But if we keep such nuclei in a strong, externally strong magnetic field, they will orient either with direction of applied field, or some of the nuclei, they will orient against the applied magnetic nuclei. So what happens due to that? So we have all this spin, we have divided into two energy levels. The lower energy levels will have the molecule, will have the spins which is aligned with the applied magnetic field, while higher energy levels will have the spin against the applied magnetic field. So when we apply very proper radio frequency, the spin which is at lower energy level will excite to the higher energy level. The energy will get absorbed. When this excited nucleus come to the ground state, it emits the radio frequency, and this light has been captured by the detector. So in NMR, we are measuring the energy required for flipping of wide variety of nucleus. Like the organic chemists use the H1, C13, nitrogen 15, 19 fluorine, or 31 phosphorus. Now, if this is the case, all protons should be come at the same place, but this is we are not observing, right? All the protons, they will, in a molecule, does not have the resonance at exactly same frequency. So why it has happening? So this nucleus of the molecule has been surrounded with the electrons. Now these electrons will also produce a secondary magnetic field, which is opposite to the applied magnetic field. So you just try to imagine a person who is wearing the sweater in a winter. So he will feel cold very less compared to the person who is not wearing the sweater. So it's the same analogy you can just try to imagine. The molecule or nucleus having the very strong cloud of the electron will be shielding them from the applied magnetic field. And this applied magnetic field will be very depending on the electron density around each of the proton. So each of this will have possess a different or it will have a different radio frequency for the excitation. You just take the example of very simple molecule like the methanol, where we have the two types of protons, the protons which attach to the methyl and proton attached to the hydrogen. Now this proton attached to the oxygen. Now this proton will be, the electron density of the proton is attracted towards the electronegative oxygen. So the hydrogen will be little bit less shielded. But if you compare to the hydrogen which is attached to the carbon, they are away from the oxygen. So we call as, so the electron density is more around these protons, and hence they are more shielded. So here in case of methanol, you will get the two signals. One signal is due to the methanol, which we call as a shielded, and another signal we call as a is due to the hydroxyl hydrogen. Friends, here the magnetic field is increases from left to right, but the shielded proton is coming near to the it's coming to the high field region. So this signal, the right one signal we call as a shielded signal. This is the shielded signal, and this one, the other one is a less shielded or de-shielded signal. Coming to the NMR spectrometer, so we dissolve the sample in deuterated solvent and place in a magnetic field, strong magnetic field. So nuclei will absorb the radio frequency, which is the radio frequency is supplied from the generator. Go to the nuclear spin will get inverted, and while coming to the ground state, they emit the radio frequency, which is captured or which is detected by the detector. With the NMR spectrometer, we can do variety of experiment like H1, C13 NMR, APT, DAPT, 2D NMR, proton NMR. You can also do 2D carbon NMR and 2D proton carbon NMR, where you can cover HMQC, HMBC, HSQC. This different type of experiment you can plan in order to get the information. Now, this is the picture I have shown of the NMR spectrometer, which is there at our center, Central Instrumentation Facility of Savitribai Phule Pune University. So for this spectrometer, we have the auto sampler of 60 samples. So we can place a 60 sample at one time and give the scanning. This is the cross-section area of spectrometer. You can see here in the center, the superconducting magnet has been constructed from some alloys, and this alloys will give the high magnetic field in presence of a very low temperature, and this low temperature has been we can achieve by having the liquid helium over here. Now this liquid helium divar has been protected by another divar which contain the liquid nitrogen. So this is the cross-sectional area spectrometer, NMR spectrometer. We have to fill this liquid helium almost 8 to 9 months in a year. And the temperature one can achieve by using the liquid helium is minus 269 degrees Celsius. To cool this liquid helium, we have to pour liquid nitrogen all the time in a divar, and liquid nitrogen will give the temperature of minus 196 degrees Celsius. We have to always take a very good precaution while filling this liquid helium and nitrogen. Liquid nitrogen we have to fill weekly, once in a week. This is the NMR spectrum I have shown. And you can see here on the x-axis, I have shown the chemical shift, and on y-axis, there are the intensity of peaks. So which information can you drag from any NMR spectra? First of all, you please count the number of signals. Number of signals indicate different types of protons, as well as location of each of the signal will give more information on electronic environment of that proton, whether the proton is shielded or de-shielded, you can get it. The intensity of protons will give the information about the number of protons of that type. The signal splitting will show you the number of proton present at just non-carbon atoms. So now the NMR spectrum is analyzed on the basis of following parameters: integration, chemical shift, coupling constant, and rate processes. Let's look at the first term, which is integration. Integration is a line. This is the line we call as integration. The area under each peak is proportional to the number of hydrogens. So integration only gives the information on relative number of different hydrogen. It never gives the absolute number of protons. I have given one example here, methyl ketone. So it gives the 3 signals, 1, 2, 3. So that means there are 3 different types of protons. Let's now calculate the integration, how to analyze the number of hydrogens. here in the first peak, you can see that there is an integration 6 mm. Second peak also has the integration 6 mm. Third peak is 4 mm. If you just add together, you will get a 16 mm. Now, the total number, if you count for this proton, is total number of protons are 8. So if you want to calculate for one proton, so one proton, the integration becomes 2 mm. So here the ratio becomes protons with the number of ratio of protons with the number of proton is 2s to 3s to 3. For example, here it's a, we already calculated one hydrogen will have the 2 mm integration. So here the 6 mm, so it will have the 3 hydrogen. In the first peak will have 3 hydrogen, second will also have 3 hydrogen. Why? The last one has the 4 mm and will have the only 2 hydrogens. Now there are quite a good number of applications if we consider the integration. For example, one can determine the proportion of given mixture of a compound. For example, if we have the mixture of two solvent, acetonitrile and benzene, and their signals are coming at 1.95 and 7.2 delta with the same integration 12 mm. So how do one can calculate the mole ratios of acetonitrile and benzene? What you have to do, friends, benzene is coming around 7.27 delta. Acetonitrile is coming around 1.9 delta. Now the protons, all the protons are of simple, same type. Even in acetonitrile, it contains only one type of protons. So integration is already given in a problem. It's a 12 mm, 12 mm. If you want to calculate per hydrogen, integration per hydrogen, it comes as a 2s/4. If you divide equally by 2, you will get the molar ratio as 1s/2. So the acetonitrile and benzene, they are present in a molar ratio as 1s/2. Next, coming to the chemical shift. The chemical shift is nothing but it's a difference between the position here, the reference position, which is having given at the 0 with respect to reference. We have to see the position of other protons. This is nothing but the chemical shift. Difference between the position of absorption of reference standard and that of particular protons. Now, which reference we have to take? So the reference we are taking internal reference is a tetramethylsilane. It should follow some of the criteria in order to have the reference standard. Which are the criteria? Your standard should be chemically inert. Then the standard should give only a single line. All the protons of standard should be magnetically isotropic. They should give a unique position, and it should be miscible with the organic solvent. It should be readily volatile in order to recover our samples, because most of the time at the last stage, we have hardly some 4 to 5 milligrams of the samples. So we have to recover the sample, and in that case, the TMS it has a low boiling point like the 26 degrees Celsius, and you will get evaporated and you will get the sample back. But why do the TMS has been coming at very shielded region? Is due to the silicon. Silicon is more electropositive than the carbon, and hence it pushes the electron density towards the carbon, making the hydrogens very, very shielded. The chemical shift you can express in Hertz as well. Chemical shift expressed in Hertz is proportional to applied magnetic field. For example, If you take the NMR, 60 megahertz NMR, the 1 delta is equal to 60 hertz. With 500 megahertz machine, 1 delta is equal to 500 megahertz. Please remember. So whenever you are expressing the chemical shift in hertz, it always depends on applied magnetic field. Here I have taken again the example of ethanol. Ethanol contains 3 types of hydrogen: CH3, CH2, and OH. 60 megahertz on 60 megahertz machine, you are going to observe the signal at 60 hertz, 216 hertz, and 300 hertz. But if you scan the same molecule on 300 megahertz machine, you will get a different chemical shift: 300 megahertz, 1080 hertz, and 1500 hertz. Please remember, whenever you are expressing the chemical shift in hertz, you will get a different chemical shift. One can calculate the chemical shift if you have the chemical shift on the 60 megahertz machine, and if you want to calculate on 300 megahertz machine, you have to use this formula: frequency of proton on A instrument into oscillatory frequency of B divided by operating frequency of A in hertz. As we already seen, when you express the chemical shift in hertz, the chemical shift will vary with the instrument. But if you express the chemical shift in delta or parts per million, it's the universal scale. Irrespective of it's a 60 megahertz, 100 megahertz, or 300 megahertz, you will have the same chemical shift. The chemical shift in delta, one can calculate by using this formula: shift in a frequency from the TMS in hertz divided by frequency of spectrophotometer into 10 raised to 6. As a delta is dimensionless, it is not proportional to magnetic field or oscillatory frequency. So delta will remain the same for all instrument. You can use the equation to calculate the delta value if you have been supplied the chemical shift in hertz. For example, if you have given a 60 megahertz machine, the methyl proton is coming on 60 hertz, and you want to calculate its a delta value in ppm, how do you can calculate? 60 hertz divided by 60 into 10 raised to 6 hertz into 10 raised to 6, it gives the 1 delta. Similarly, for the methylene proton, if you are getting a chemical shift at 216, how do you can calculate chemical shift in delta? 216 divided by 60 into 10 raised to 6 into 10 raised to 6, you will get 3.5 delta round. So higher the chemical shift in hertz or delta, de-shielded is the proton. Lower the chemical shift in hertz or delta, shielded is the proton. These are the different regions of chemical shift. Generally, this region, the region towards the TMS is coming at 0 hertz or 0 delta. You will see this region we call as a shielded region, and if we are going towards the 10 delta, we call as a de-shielding region. Now between 0 to 2, we can have the protons present in an aliphatic system, beta substituted aliphatic system. From 2 to 3, you will get a protons from alkynes. For alkenes, one can see the region from 5 to 8. Aromatic protons are coming from 6 to 9, and the aldehyde proton is most de-shielded proton, and it comes around in between 9 to 10. The chemical shift has been, it's depend on the electron density around that proton. If that proton is attached to electron withdrawing inductive group, that will be get de-shielded. Let's take the first example. Here the methyl is attached to the alkanes, methylene is attached to the alkanes, and methine proton, 3 types of protons. The methyl protons comes around 0.9, methylene protons comes to 1.3, methine proton 1.7. Coming to the next, the methylene protons attached to the iodine, methylene proton attached to the bromine, methylene proton attached to the chlorine. So as you know that the electronegativity is increases from iodine to bromine to chlorine, this proton will be de-shielded due to the electronegativity of these halogen atoms. Hence, the methylene attached to the chlorine is much de-shielded and it's come around 3.7 as compared to the methylene attached to the iodine, which is coming at 3.2. Similarly, same type of electron withdrawing inductive effect you can observe for second set of molecules, where the methyl is attached to the oxygen, methyl is attached to the nitrogen, methyl is attached to carbon. The electronegativity is increases from carbon to nitrogen to the oxygen, and hence the delta is also increasing. The proton become a more and more de-shielded. So you can have a variety of your, you have to remember this table, and whenever you are analyzing some spectra, a real proton always come between 7 to 9. The proton attached to the alkyne coming around 2.5 to 3, while the olefinic proton is always come more than the 5. Also, please remember the protons which are attached to the electronegative atom like nitrogen and oxygen, they are called as exchangeable proton, more acidic proton, and hence they are de-shielded and coming at very high delta values. Particularly the proton attached to the acid, carboxylic acids, come between 10 to 12. And in order to confirm whether they are exchangeable protons or not, one has to do the deuterium exchange test that I'm going to explain in the next slide. Next is spin-spin coupling. We have to explain over here. Here I have given again the example of ethyl-methyl ketone. It contains 3 types of hydrogen. So 3 peaks you are going to observe. Now the 3 groups, so it contains 3 groups of non-equivalent hydrogen. Now these signals, you can see the first signal is showing the 3 lines, which you call as a triplet. Second signal is showing only 1 line, while the third signal is showing the 4 line, which we call as a quartet. Now, why do we are observing this splitting of signal is due to the spin-spin interaction with its neighboring proton. The spin-spin interactions occurs between only a non-equivalent protons. Please remember. So from this coupling constant, one can determine the coupling partners. Now, what is a coupling constant? Coupling constant is a distance between 2 lines in a multiplet. The coupling constant is always expressed in Hertz. It is independent of operating frequency. Please remember, students, the midpoint of this multiplet we are mentioning as a chemical shift. It's a midpoint. This is a quartet and triplet. In case of triplet, the line position of the middle line will be indicated as a chemical shift. So whenever we have the single proton with no neighboring protons, you will always get a singlet. When we have a one neighbor, you will get a doublet. When we have the 2 neighbor, when HA proton has the 2 neighbor, you will end in a triplet. When you have the 3 neighbor, you will get a quartet. But please remember, the students, their intensity as well. The doublet always shows the intensity 1:1, triplet 1:2:1, quartet 1:3:3:1. So how one can calculate the intensity of this multiplate? Before that, let's have the different types of coupling. It's a geminal coupling, vicinal coupling, long range coupling. What's meant by geminal coupling? Means both the protons, when they are attached to the same carbon, we call as a geminal coupling. It is also called as a 1,3 coupling, because if you try to label these protons, 1, carbon 2 and proton 3. So it's a 1,3 coupling or 2 bond coupling. Next come to the vicinal coupling, which is also called as a 3 bond coupling or 1,4 coupling. You may also observe 1,5 or 1,6 coupling, which we call as a long range coupling. The coupling between nuclei separated by more than 3 bonds, we call as a long range coupling. Again, please remember the coupling constant is always expressed in a hertz. It is independent of oscillatory frequency. One should follow the first order analysis rule. So what is mean by first order analysis? The first order analysis means if you take the two chemical shift, which is expressed in a hertz, their chemical difference, and divided by the coupling constant. And if this ratio is coming greater than 6, then we call as this is the first order analysis. What are the rules for this first order analysis? The first rule says that equivalent protons do not couple with each other. Second rule is the rule to calculate the maximum number of lines one can expect for particular protons. How do one can calculate? You can calculate by using the formula 2Na into Ia plus 1, 2Nb Ib plus 1, 2Nc Ic plus 1, where Na, Nb, Nc are number of neighboring non-equivalent nuclei, and Ia, Ib, Ic are the spin numbers of respective nuclei. In case of hydrogen 1, carbon 13, nitrogen 19, fluorine 31, phosphorus, we have the spin number 1/2. And if you fill the spin number in this equation, you will simplify the equation as Na plus 1, Nb plus 1, Nc plus 1, and so on. When the multiplicity is produced by a group of equivalent nuclei with I is equal to 1/2, the intensity of different lines, one can get it by solving the expression x plus 1 raised to n, where n is number of interacting nuclei. This is the Pascal triangle, which is very famous to calculate the intensity of multiplate. Whenever you have the signal doublet, it gives 1:1. With triplet, 1:2, 2:1. With quartet, 1:2, 3:2, 3:1. With quintet, 1:2, 4:2, 6:2, 4:1. In Pascal triangle, you have to write in the first column, it's not column one can see, but 1, 1, 1 you have to write, and then middle number you can get it by addition of the remaining 2 digits. Now, you just see the, may I request the participants, you can ask the queries in a chat box so that the coordinator will contact with me later on. So this is the multiplate. Let's calculate. This is the very good example I have given over here. Here we have taken the 2 different molecules. It's a 1,2 disubstituted benzene ring and 1,3 disubstituted benzene ring. Now I have color one hydrogen with the red color. So this red color hydrogen, how much lines it will show? Let's find out its coupling partner. It's coupled with its neighboring proton, which is ortho to this. And it also coupled with other neighboring proton, which is ortho to this. Both are ortho, hence they will couple with the almost 8 Hertz coupling constant. As the coupling constant is same, and there are 2 neighbored, so 2 plus 1, you should get a 3 lines. But again, these 3 lines will couple, this red proton will also couple with the meta proton. with the 2 Hertz coupling constant. So each of these 3 lines will again divided into doublet with the meta coupling. And the same result you are getting over here, which we called as triplet of doublet. Why do we say it's a triplet? Because there is the first coupling constant is 8 Hertz, and we have the 2 protons with which it's coupled. So it gives the triplet, and each of the triplet will further divided into doublet by the coupling with the meta. So this signal 6 lines we call as a triplet of doublet. In case of 1,3 disubstituted benzene, this red proton will couple with its neighboring orthoproton with the 8 Hertz coupling constant. So you will get a doublet, but this red proton will also couple with the 2 metaprotons. Now they are metaprotons, so the coupling constant should be 2 Hertz. So each of these doublet will again divided, each of the line in a doublet is again divided into 3 lines. So what the pattern you are getting, we call as a doublet of triplet with the coupling constant 8 and 3 Hertz. Here also the coupling constant is same, but here in the first molecule we have the 2 orthoprotons, in the second molecule we have the 2 metaprotons. This is the coupling constant values. Vicinal proton generally gives the coupling constant around 7 Hertz. The protons which are attached to the olefin, we call as olefinic proton. These are the trans protons. So the trans coupling constants come around 11 to 18 Hertz. The cis protons will come around 5 to 14 Hertz, while the protons which are attached to the in the inner ring and they are olefinic, it also shows 8 to 11 Hertz coupling constant. The geminal proton, olefinic proton shows a coupling constant, very less coupling constant, 0 to 3 Hertz. While sp3 geminal coupling constant is coming, it's very high and it comes around 11 to 18 Hertz. In case of aryl protons, when they are ortho to each other, they shows 8 Hertz with the meta coupling constant 2 Hertz and allylic coupling constants between 4 to 6 Hertz. In the next example, I have shown a cyclohexane ring. In the first ring, we have the 2 protons which are trans to each other, axially oriented. It shows a coupling constant 7 to 10 Hertz. In the next structure, you have both the protons equatory oriented. It shows the 5 Hertz. And in the last one, you have the one axially oriented, one equatory oriented. It shows coupling constant between 0 to 7 Hertz. So why do the coupling constant varies from axially oriented, equatory oriented, and axially equatory oriented? So this factor is depend on the coupling constant is depend on the dihedral angle. Dihedral angle means the angle between hydrogen, carbon, carbon, hydrogen. It's just like you just open the book and you will get the dihedral angle like this. On the one page, you will get one CH, and another page, we will get the another CH. And in between the angle, we call as a dihedral angle. So this relationship between dihedral angle and the coupling constant has been given by the Karplus equation. When we have the dihedral angle 90 degree, we get the 0 coupling constant. While when we have the 0 and 180 dihedral angle, maximum coupling constant, you will get it. Next, we will see the dynamic process in NMR. Dynamic process means it always you have some reaction is going on and you want to observe some changes, then this dynamic processes you can visualize with the NMR. Some of the example I would like to give over here. Intermolecular proton exchange one can be very well studied by using NMR, rotational about carbon-carbon single bond, rotation about the double bond, inversion at nitrogen and phosphorus atom, ring inversion, ketoenol tautomerism, reaction and equilibrium processes, etc. Coming to the first dynamic process is exchangeable proton, which is present with the amines and alcohols and acids. In the last slide also, we have given the NMR of ethanol. In ethanol, you are observing one triplet and quartet for the methyl and methylene proton. Hydroxyl proton, you are not able to see over here because here we have done the D2 exchange test. But if the same molecule, if you purified, we removed all the acidic and basic impurity and make it very extra pure, you will see the 3 signal, and the middle signal is little bit complex. It shows something 8 lines. Why do it shows 8 lines? Because it couples, this signal is due to the methylene proton. This methylene proton will couple with the methyl proton. It also couple with the hydroxyl proton. So the total 8 lines you will observe for the methylene, while the hydroxyl proton will also couple with this methylene proton, showing the triplet. This is very, very extra pure ethanol, no traces of water, no acid and bases impurity. So why do you are observing? It's because this protons, acidic proton, it always exchange, it forms the hydrogen bonding with the another molecule. And okay, in the first molecule, you have the red hydrogen. Another molecule, it will pick up the blue hydrogen and convert into another. So that this hydrogen is not remaining the same all the time. It always exchanges. So the spectrometer is not able to recognize this exchangeable protons. One can identify this acidic proton, OH or NH proton, by doing very simple test, which we call as a deuterium exchange states. What you have to do, you have to add 1 or 2 drops of deuterium oxide in a sample, shake the tube and again scan the sample. In the second scan, if the peak is absent or it is much less intense, then you say that that peak is belong to the OH or NH. In the next slide, I have shown you the chemical shift and type of hydrogen bonding. Now here, the right spectra is due to the ethanol and the left spectra is due to the orthohydroxybenzaldehyde. In orthohydroxybenzaldehyde, we have the intramolecular hydrogen bonding. So even if you dilute the sample, intramolecular hydrogen bonding will not break. So the pattern will remain same in an intramolecular hydrogen bonding. But if we have the intermolecular hydrogen bonding, like in the case of ethanol, this is the neat sample where the hydroxyl proton is coming around 2.5. If we add 5% of CCl4, you are getting, the sample is de-shielded. Why? Because hydrogen bonding is forming and the sample will get de-shielded. Please remember, students, this OH, NH proton, their chemical shift is always depend on the concentration, solvent and temperature. Next example is NN-dimethyl formamide. This NN-dimethyl formamide at room temperature, if you see the sample, you will see the 3 signals, 2 sharp singlet and 1 very de-shielded signal, which is due to the aldehydic proton. But this methyl protons, they are showing a 2 different signal. Why they will show the 2 different signal? Because of this resonance. If you pull this pi electrons on oxygen, the lone pair of nitrogen will shift over here and you will get this resonance structure. Now, to this resonance structure, one methyl is cis to the O minus, while another methyl is trans to the O minus. So in this way, these 2 methyls, they are non-equivalent methyl, and hence you are getting a 2 different lines for 2 different methyls. When you scan the same molecule at high temperature like 120 or 160 degrees Celsius, the doublet is coalesces to a singlet. It converted into a singlet. Why it happens? Because at high temperature, the carbon-nitrogen rotation, is very, very rapid. And in that case, both the methyls will not differ into each other and the doublet will merge into a singlet. Into the very important part of the this talk is interpretation of NMR spectrum. The first hint let me give. You just, whenever some NMR spectrum will comes to you, you just count the number of signals. The number of signal will tell you the number of protons, number of different types of protons present in the molecules. Same thing is true for the carbon. Number of carbon is equal to number of signals is equal to number of chemically non-equivalent carbons. Now let's look at this first example of chemically equivalent protons. The first you're getting this acetone, dimethyl ether, and the last one. All these XYZ 3 sets of molecule will contain only one type of proton. They are not chemically different. So what is mean by the chemically equivalent proton? That are the protons which shows the same chemical environment, therefore they will come at a same chemical shift. They do not couple with each other. Please remember, equivalent protons will not couple with each other. How do you are going to identify them? You just replace each of the proton with some phantom atom. If you are getting the same compound, you should say that the hydrogens are chemically equivalent. In the next example, it's a ethyl chloride. It contains two types of protons, so two signals you are going to observe. Diethyl ether, again these two methylene protons are same and two methyl proton are same, so two signals you are getting, you will get it. In ethanol, there will be three signals: hydroxyl, methyl, and methyl. In the next example, it's an anisole example. So the protons which are ortho to methoxy groups, both the protons, they will come at one position. Metaproton will come at one position and paraproton will come at one position. So please look at the symmetry over here. If you put a line between this first carbon and the fourth carbon, you will get a symmetric molecule. So orthoprotons are same, metaprotons are same, and paraproton is one more pick, you will get it. So total signal you will get for anisole are 4. For 1,2-dimethoxybenzene, you will get total 3 signal. Next, 1,3-dimethoxy, you will get the 4 signal. How? The first signal, which is de-shielded over here, this proton, the proton is which is sandwiched between two methoxy groups, will give 1 signal. This 2 will give 1 signal, and this metaproton will be the another one. So total, and apart from this methoxy, total 4 signal. In case of 1,4-dimethoxybenzene, you will get both the dimethoxy will come at one position, and all these 4 protons will be equivalent protons and will come at one position. So total 2 signals you will get it for the last compound. You may also observe a stereochemical non-equivalence. So what is meant by stereochemical non-equivalence? Suppose you take this example here, the 2 protons are attached to the same carbon, but they are not equivalent. Why they are not equivalent? This Hb proton is trans to the Ha and cis to the aryl ring, while Hc proton will have aromatic ring trans, but at cis position it have Ha proton. So all the 3 protons are non-equivalent in case of, this is the styrene example. Similarly, the protons which are attached to this carbon, Ha and Hb, they are differ because Hb at one side it has because the next carbon is a chiral carbon. What is a chiral carbon? Carbon attached to the 4 different groups: hydrogen, methyl, chlorine. So this is the chiral center. So please remember, whenever you have the methylene protons next to the chiral center, we call as a distereotopic protons, and both protons will give a separate signal in NMR. Similarly over here, in case of pentanol, the HD and HC will show they are non-equivalent protons and coming at different positions. Please try to identify the number of signals in H1 NMR for total number of signals. The first compound will give the 2 signals, second compound 2, third compound will give the 4 signal because this is a chiral center, and the last one will give you 3 signals. Ha proton is cis to the chlorine, Hp proton is cis to the trans to the chlorine, while this proton is geminal, is attached to the same carbon where the chlorine is attached. So total 3 number of signals you will get it for the last compound. This is the one more example, N-benzyl 2,6-dimethyl piperidine. The two structure for you, they are not same structure because in the first structure we have the 2 methyls, they are cis to each other. In the second structure we have the 2 methyls, they are trans to each other. Now we have to look for the HA and HB signal, whether they are equivalent or non-equivalent. So the first one will give both the HA and HB will come at one position, while in the second one, HA and HB will come at 2 different positions. And these 2 protons we call as a distereotopic proton, while HA and HB in a cis compound we call as an enantiotopic proton. If you draw the conformation, chair conformation of this compound, you can immediately understood what I would like to mention over here. Here, both the methyls, they are equatorial, and you can imagine a symmetry which is going from the nitrogen and 4th carbon. In this case, 2 methyl, one methyl is axially oriented, other is equatorial oriented. You don't have any symmetry over here. So both the HA and HB will appear differently. Coming to the next topic is a magnetic equivalence and non-equivalence. Up till now, we have understood chemical equivalence. Now let's look at the magnetic equivalence. When the 2 equivalent nuclei, they have the identical relationship, so they will have the same chemical shift, we call as a chemical equivalent. Now in the magnetical equivalent means 2 equivalent nuclei, they will have the same coupling relationship with their identical partner are called as magnetically equivalent. The magnetically equivalent nuclei will have the same chemical shift, same coupling constant with same partner. Take the example over here. It's a 1,2,3 tribromobenzene. Let's look at the H2 proton. H2 proton will couple with H3, H2 proton also couple with H1. Both are orthocoupling constant with, so coupling constant will be around 8 Hertz. So the coupling constant is same. So H2, so H1 and H3 are called as a magnetically equivalent proton. Let's look over here. Now here, how many signals do you want? You will get it. H1, H5 will resonate at one position. H2, H4 will resonate at one position. H3 will also come at the one position. Now H5 will couple with H4 with orthocoupling constant. H5 will couple with H3 with the metacoupling constant. H1 will also couple with H2 with the orthocoupling constant, which is 8 Hertz. H1 will also couple with H3 with metacoupling constant. But if you want to calculate coupling constant between H1 and H4, they are different. They are paracoupling and very less. Take the example over here. Is a magnetically, I will give more emphasis on the magnetically non-equivalent protons. Here, 1,chloro,4-nitrobenzene. It shows total, this is the spectra for the aryl protons. Please remember the protons which are attached to the, which are nearer to the nitro groups, they are de-shielded and come around 8.1, while the proton which is ortho to the chlorine, they will come around 7.5. Now, how many signals you should get it? Only 2 lines, right? These 2 protons, ortho protons to nitrogen, they are same. Ortho to chlorine, they are same. So you should observe only doublet, 2 doublets. But what you are observing, it's something different. Why do you observing? It's due to the magnetic non-equivalence. Please remember, okay, this proton is coupled with its ortho partner with the 8 Hertz coupling constant. This proton will also couple with this coupling constant with 8 Hertz, but if you see this proton, when it try to couple with this, it has the para coupling constant. It is the, so coupling constant does not remain same. So this proton we call as a magnetically non-equivalent protons. They are chemically equivalent, but magnetically non-equivalent protons. Here again, the same thing, I would like to emphasize more on the magnetically non-equivalent protons. Now let's look at the next. Again, try to identify the number of peaks. You will get it from the scanning this compound. You should get only 2. From this, you should get 3. From the next structure, how many you should get it? 1, 2, 3. No, you should get the 4. How they are 4? Methyl will come at 1. The proton which is attached to the same carbon will give 1 signal. But these 2 protons are equivalent protons, and these 2 protons, beta protons, they are equivalent. So total 4 sets of signals you will see for the in NMR spectra. In case of paramethoxy-toluene compound, you should get again 4 signals. This is again a structure, this spectrum for the 4-methyl benzaldehyde, the aldehydic proton, which is much de-shielded, come around 9.8. Methyl proton is shielded proton coming around 2.5, while the aryl protons both are giving different signal at 2 position between 7 to 8. Now let's look at do some actual interpretation of NMR spectra. I have given you one NMR spectra and also given the molecular formula. Now how to drag the information from the NMR spectra? Madam, how much time I have? Hello?
Hello?
How much?
Another 5-10 minutes, ma'am.
Okay, fine. So you are observing the 3 signals over here. I have directly given here the integration, 9 hydrogen, 3 hydrogen, 2 hydrogen. Now the molecular formula is a C7H14O. The first step you have to do is to calculate the site of unsaturation or hydrogen deficiency. How to calculate? Whenever the molecular formula contain oxygen, you just eliminate oxygen and calculate the site of unsaturation. When the halogens are there, you try to add 1 hydrogen. And when you have the nitrogen, you subtract 1 hydrogen from the molecular formula and try to calculate the site of unsaturation. For example, C7H14. Now, if carbon 7, and if you want to form the saturated compound, you should follow the empirical formula C and H twice N plus 2. So with the C7, you should get 7 into 2 plus 2. So total you should get 7 into 2, 14, 14 plus 2, 16. But how many hydrogen are there? There are only 14 hydrogen. So 2 hydrogen are less. So 1 site of unsaturation. Now you are getting a 3 signals, means you will have the neighboring carbon does not carry any proton. Now the first signal is for 3 hydrogen. Please remember carbon valence is 4, so none of the carbon will have the more than 4 substituent. So there must be 3 methyl groups which are equivalent. So you have the 3 methyl group which is attached to same carbon. And then we have at 2.2, you have the 3 hydrogen. So there must be the hydrogen attached to the next to the carbonyl group and then come to the CH2 group. So the answer is this one. So all these 3 methyls, they are equivalent. Their neighboring carbon does not carry any hydrogen, so they will give the singlet around 0.9. Within proton, they are mostly shielded, so they come at around 2.4, while the methyl protons will slightly shielded than the methylene proton and comes around 2.1. In the next signal, you have the molecular formula C2H5Br. So it's a halogen, you have to add 1 hydrogen, the formula becomes C2H6. It's a saturated compound and you are observing 1 triplet, 1 quartet. Triplet means neighboring carbon should carry a total 2 protons, while the quartet means neighboring carbon should carry a 3 protons. So this is the example of bromide. Next is the example, take the example C2H4Br2. 2 signals you are getting, again this contain C2H4Br2. For 2 halogens, add 2 hydrogen, you will get C2H6. And hence this is a saturated compound. The first signal is doublet, means its neighboring carbon should have only 1 hydrogen. Another signal is quartet, so it should attach to a carbon which carries a 3 protons. So the signal, this is the 1,1 dibromoethane. Next example is C2H4O2. You are observing a 2 signal, one at 11.5, another at 2. Please remember to calculate the number of protons under each of the signal by observing the integration. Please calculate the number of protons, and what you are getting the formula by solving the equation, it's an acetic acid. In next, C4H8O2, 3 signals, and it's due to the ethyl acetate. I would like to go further, and lastly, I would like to show this signal. This is the H NMR spectrum. I have taken on 400 megahertz machine at our chemistry department. Now the molecular formula is C8H7Br and O. I already told when the oxygen is there, please neglect the oxygen. Your formula turns to be C8H7BrO. Now halogen is there, so the formula now turns to be C8H8. Now please calculate the site of unsaturation or hydrogen deficiency. Total it founds to be the 8 hydrogen are less, so the 4 site of unsaturation are there. Now you are observing 3 signals, only 3 signals. That means it contains only 3 different type of hydrogen. Now this number is indicating the integration. Now the software is there available with us, so you don't have to calculate the height of the integration. You directly get the digit over here which indicate the number of protons. So 3 hydrogens are coming over here. 1.96 2 hydrogen. This is signal for 2 hydrogen. This is signal for 2 hydrogen. Total 4 site of unsaturation. Please remember, think about the aryl ring. Now it's a disubstituted ring. How do you see it's a 1,2 disubstituted or 1,3 disubstituted or 1,4 disubstituted? When we see it's a 1,2 disubstituted, you should get 1, 2, 3, 4 different signals, but you are getting only 2 signal. In case of 1,3 disubstituted, you will get 1, 2, 3, 4 signal, but you are getting 2. In case of 1,4 para substituted, these protons will come at same position, this proton will come at same position. So 2 signals you should get it. So, and you are getting only 2 signal, that means this is a para disubstituted. Then how to calculate its coupling constant? How do you will do it? You have to take this, these are the line position, exact line position for the one doublet, which is a 7.84 and 7.816. Take the difference and you just multiply, as this spectra is I have conducted on a 400 megahertz machine. So the difference is multiplied by 400, you will get the coupling constant, which is coming between 8.2 to 8.3 hertz. So the the signal which is correspond to 2.59 is for the 3 proton. That means you have the 1 methyl group which is attached to the aryl ring, benzene ring. Or now, sorry, it's not benzene ring, it's a oxygen is there, so it's a acetophenol. And at para position you have the Br. So this is the structure of para-bromo acetophenol. In the next, you have the formula C6H6N2O2. Now, again, you are getting a signal, only 2 signals, around 6.61 signal, around 8, another signal in between. Okay, this the first signal is due to the TMS. The second signal which you are observing at 1.5, it's due to the water present in a solvent. What the solvent you have used is a CDCl3. CDCl3 is coming around 7.27, and whenever moisture is present in a CDCl3, you are getting a peak around 1.3. So these are due to the 2 solvents present over there. Now, this signal has been vanished when you exchange when you add the D2O and rerun the spectra. So this signal will get vanished. So these 2 protons are exchangeable protons. Now coming to these 2 signals, the most deshielded signal is coming around 8 megahertz. So it's a very deshielded. So that means its neighboring carbon should have some electron withdrawing group, while the another is 6.6 some signal is coming, which is a shielded than the benzene proton. That means this nearer to this proton, we have some electron donating group. Now, as it contains the 2 nitrogen, immediately you should keep in the mind there are 2 functional group of nitrogen which withdraws electron density, which is a nitro group, and which the another functional group of nitrogen, which is amine, which donate the electron density. So the structure of the compound is nitroaniline. This is the structure NMR spectrum of orthocresol. The OH group is confirmed by the D2 exchange test. This is the isocoumarine compound, which shows the 1, 2, 3, 4, 5, 6 signals, which you can assign to different protons attached to in this structure, and they are like this. Now, in the next coumarine structure I have given, you just try to identify which proton will be deshielded, where H3 or H4. So H4 protons will be deshielded because of it's a beta to the carbonyl. If we withdraws the electron density and write the resonance structure, the positive charge will be generated at the beta, and hence this proton, H4 proton, is de-shielded and coming in the de-shielded region. Let me wind up my lecture. I'm very thankful to organizer for inviting me for delivering the lecture over here. This is the photograph of NMR facility, which is available at Central Instrument Center at Savitribai Phule, Pune University. You all been invited to look at our Central Instrument facility. We have, apart from the FT NMR 500 megahertz NMR, we have the HPLC, LCLC, LCMS, X-ray crystallography. We have the same. So very sophisticated instruments are there. Please visit our department. I have given my email ID as well as my YouTube channel ID also I have given. Thank you all of you for your patience.
Okay. Thank you, Dr. Vaishali Shinde. It was a superb and excellent presentation of all the concepts you have explained in a very lucid manner. And we all were looking forward for your presentation, and you have nailed it today with your special knack of presentation as well. And तुम्हाला doubt होता कि you are taking a post lunch session, and so how the students or participants, everybody will be interactive. But
I really don't know whether they are really have the
all the delegates. All the delegates have interacted. I mean, they were so alert, madam, and there are many questions and queries raised by the delegates. And in fact, if there was any award, for the participant who has raised many questions, then it definitely goes to somebody who's known as Vikas Khatik. N number of queries he has raised, and I think he should be contacting you directly. Though I will take a few questions.
Please share my email ID.
Yeah, I'll take a few questions, madam, and organizers as well as, of course, you can stop me at any moment, and you just tell me how many questions I can take up. So the first question I will take is, in different NMR spectroscopy, why does chemical shift values ranges differ? This is by Vishal Kamath. In different NMR spectroscopy, why does chemical shift value ranges differ?
I already answered that question.
Yes.
The chemical shift you can express in hertz as well as in delta, parts per million. When you are expressing in hertz, the chemical shift will depend on oscillatory frequency of that machine. So if you scan the same NMR on 500 megahertz machine, the 100 megahertz and 500 megahertz, both the chemical shift will differ. But if you are expressing the chemical shift in delta or parts per million, the chemical shift remains same.
Okay. The next question is from Monica Umbre. How to determine purity of deuterated solvents by NMR spectroscopy?
Okay, for example, for CDCl3, this is the most common solvent we are using in NMR. Okay, none of the students have asked me, if you are using deuterated solvent, why do you are observing a peak? The peak, it's not 100% deuterated solvent. It's maybe 99.5 or 99.9%, and whatever the traces are there, they are protonated solvent. So you will always get a signal due to the protonated solvent. And now this CDCl3, it's a hygroscopic solvent. It always absorbs. Whenever you open the bottle of CDCl3, it will absorb the moisture from the air, and water peak will appear around 1.5. So appearance of many peaks, apart from the solvent, observing in a spectrum, it indicates that the solvent is impure.
The next is Snehal Pardeshi and Purva, and both would like to know why only TMS as standard. If you have answered this.
Yeah, I already given the answer, because the criteria, if some compound has to be standard, it should follow some criteria, and the criteria has been very well followed by the TMS. So the TMS is a solve. But okay, in very specific research, we may use some other standard as well, apart from the TMS. And though here I have shown the NMR spectrum from 0 to 10, but it may go to up to 15, depending on kind of the proton, whether it is a shielded, de-shielded, and some proton will have the negative delta value as well. So it all depends on environment around that proton.
Next is, our advanced analytical techniques can give the full picture of the complex herbo-mineral formula of Ayurveda.
No, it's not a, okay. If
this is by Mr. Vikas Khatik again, yeah, okay.
Okay, if the compound is highly pure, I'm again saying with the compound is highly pure, then only you can analyze the sample. If it is a mixture of 2-3 molecules, you never able to end in a some structure. So first, try to pure the samples. The purity you can check by the different, maybe the TLC, or if TLC you will getting a single spot. Sometimes the RF values of 2 molecules are also coming the same, so you can separate with the column. This also happens. The first needed thing is you have to purify the samples, and then you can analyze the structure. But again, you should know them. You should have in your hand molecular formula, and one can get the molecular formula by doing the mass spectrometer. You will get the molecular formula in your hand, then you can relate with pick appear in a H1 spectrum.
Can I take up 1 or 2 questions, ma'am?
Yes, sure.
Okay, so tell us something about methods of solvent preparation and amount of sample required for H1 NMR. This is by Pratik Panchbhai.
For H1 NMR, you require hardly 4 to 5 milligram of sample. For carbon, you require 15 to 20 milligram of samples. As we are not analyzing carbon 12 nuclei, carbon 13, the natural abundance of carbon 13 is very less, around 1.1%. So you, for carbon 13, always you require
what is the
and for
best?
one sample, you require hardly 0.5 to 0.6 ml of sample.
Okay. The next one again from Vikas Khatik, and it is, what is the best choice to normalize serum samples to be analyzed by metabolomic approach using NMR? Best choice to normalize serum samples to be analyzed.
Okay.
He can come back to you later.
Yeah, sure. Because for this type of problem, you have to go for the 2D NMR.
Hello, Dr. Chitri.
Yeah.
I request Komal Sonamne madam to take over.
Yes, ma'am. I think the question and answer session is over, and the remaining questions will be taken up and will be sent by the mail to Vaishali ma'am, and we'll get back to you with the answers to the participants. Now it's time for a feedback from the participants. So I would like to call upon Dipali Bhandari ma'am to share her feedback about the session.
Hello.
Ma'am, you can.
Yeah, am I audible?
Yeah, you are audible.
Yes, good afternoon, ma'am. I Ms. Dipali Bhandari, Assistant Professor in Dr. M.S. Gosavi College of Pharmaceutical Education and Research, Nasik. I would like to thank you for organizing the most wonderful today's webinar on this such a wonderful topic of spectroscopic techniques for the structure elucidation, which is little bit difficult but quite interesting actually. But all the honorable speakers, Dr. Uday Devkate sir, Dr. Bhagat sir,
Hello.
Yes, Deepali.
I think she got disconnected. Uh, so now I would like to call upon Deepak Patil sir to share his experience about this seminars.
Good afternoon to everybody. Myself, Dr. Deepak Patil, Associate Professor at HR Patel Institute of Pharmaceutical Education and Research, Shirpur. I feel very lucky to be a part of this series of webinar that is use of spectroscopic technique conducted by AISSM Pune. In first session, Dr. Devkate provided the valuable input about the basics and the practical application of PLC. In second session, Dr. Bhagat revised the basics of both the spectroscopy, UV and IR, UV visible and IR spectroscopy, along with their practical application. And what the today's session that is by Dr. Shinde, she covered the basics of NMR, then history, then Nobel Prize scientist, then principal instrumentation, and a much more broad aspect of practical application of NMR. I hereby thank the organizers of the AISSM for conducting such a wonderful seminar. Thank you. Thank you very much.
Thank you, sir, for your valuable feedback. Now I would call upon Dr. Poonam Inamdar ma'am to share her experience.
Hello, am I audible?
Yes, yes, ma'am.
Yes. Good evening to all the dignitaries and the participants present here. I, Dr. Poonam Inamdar, am immensely happy to share my views regarding this webinar series. AISSMS College of Pharmacy had always been one of the prime institutes giving importance to the advanced learning, and definitely this webinar is an outcome of that. The webinar had a theme of how to use the different spectroscopic techniques for the structural elucidation as well as the characterizations. Okay. Then therefore,
Poonam,
Ma'am,
unmute
please unmute
yourself.
yourself.
yes. The theme was very much intriguing and the sessions were very informative since yesterday Dr. Uday sir, Dr. Bhagat sir, and today Dr. Vaishali madam. The knowledge, whatever they have shared with us and even with the different students as well as the faculties will be definitely helpful to carry out their research and their dissertation things and the faculties who are recently starting to write the research grants. I would like to express my heartfelt gratitude to the organizers, Principal Dr. Madgulkar Madam, Co-Coordinator Dr. Shikant Bhandari Sir, and to all the team members and the faculty members of the AISSMS College of Pharmacy for organizing such a flawless webinar series. Thank you so much for giving us an opportunity to be a part of this webinar series. Congratulations to the team. We will look forward to join AISSMS College of Pharmacy team members in future if they're going to conduct such kind of informative and educational sessions. Thank you so much.
Thank you, ma'am. Lastly, I would call upon Satrupa Acharya ma'am to share her views.
Yeah, am I audible?
Yes, ma'am.
Yeah, good evening to all. First of all, I would like to express congratulations to the team AISSMS College of Pharmacy, our organizers, Dr. Madgulkar Madam, Coordinator Sir, Bhandari Sir, and the whole team for organizing such a seamless, beautifully organized lectures. And the topics of the lectures were so apt and so relevant to the current times. And we know as a pharmacy student, as a student in the long time journey of pharmaceutical industry, that the importance of these techniques are the importance of learning these concepts is so much important for building up a good career in not only in professional but in industrial, but also as an academic career. So I would like to say special thanks to today's speakers. The speakers were all very experts in their own fields. And I would like to express a special thanks to Dr. Shinde today for such a lucid delivery of not so easy concept, that is NMR, and making us awake during the whole period. And thank you, ma'am, for taking us from the history to the applications of NMR in such a beautiful manner. So I would like to express my heartfelt thanks to all of you, and we look forward to more such intriguing seminars in the coming time. Thank you, ma'am. Thank you all.
Thank you, ma'am, for sharing your valuable feedback. Now, I take this opportunity to propose a vote of thanks. So, I, Komal, on behalf of AICSMS College of Pharmacy, I wish to express heartfelt thanks to our distinguished speaker, Dr. Vaishali Shinde, ma'am, for delivering such an informative session and sharing her expertise on role of H1 NMR in structure elucidation. I would like to thank our previous session speakers, Dr. Uday Devkhate sir and Dr. Kundalik Bhagat sir, for accepting our invitation as a resource person and sharing their valuable knowledge and expertise with us. I would like to express our gratitude to Honorary Secretary Shri Maloji Raji Chhatrapati and other office bearers at AICSM Society. I thank our principal, Dr. Ashwini Madgulkar ma'am, for her encouragement and constant support. I extend my special thanks to all the participants who have turned up in such a great number and for their active participation during this seminar. I would especially thank to all the participants who have given their valuable feedback for this session. I would also like to thank the media team at the AICSM Society and our college. Lastly, I'm very much thankful to the coordinator of this seminar, Dr. Shashikant Bhandari sir. And as well as we all know that no program is successful with a single person. So I extend my big thanks to all the staff members of the chemistry department, as well as all the staff members who have directly and indirectly helped us to make this seminar a great success. Now, once again, I thank you all for making this seminar a successful event by your contribution. And reminder to all the participants, please fill up the feedback link which is shared in the chat box. And after filling up the feedback form, the e-certificate will be generated and shared to your registered email address within 1 week of time. Thank you. Thank you once again.